Okay, so we have gone through the review part, and now we're going to look at some regular exercises, but they are just as easy. Okay? So here we go. Number 7.1, we're on the back of page 12. 7.1, we're going to roll a die. Now, the study of probability assumes that you are somewhat familiar with dice, what they look like, little cubes, dots on them, and that you're familiar with a deck of cards. We'll be doing some card problems later. So if you're not comfortable, like if you don't know anything about a deck of cards, you might want to go home and kind of just look through one. So when we talk about what's the probability of drawing 2 kings, you'll know what we're talking about, and you'll be able to work it out. Because it's hard to do the math if you don't understand what a deck of cards is like. So spend some time with that if you need to. Now, everybody knows what a die is. We're going to roll it. There's a 1/6 chance of getting any particular number, right? But I want a factor of 24. So keeping in mind that these are the possible outcomes, how many of those are factors of 24? All of them except 5. Aren't they all don't they all divide into 24?
Yeah.
So if I roll this die, the probability of getting a factor of 24 is going to be 5/6. Because 5 of the numbers are factors of 24, and there are 6 possibilities. A prime number. Now remember, from now on, you're expected to know 1 is neither prime nor composite. 1 is not part of the conversation. So of the remaining ones, which ones are prime? 2, 3, and 5. So the probability of getting a prime number would be 3/6 or 1/2, or if you prefer 50% or 0.5, right? All of these are perfectly fine ways of writing a probability. Why didn't I do that with this one? I'd have to round it off, and we don't like that. If you can avoid rounding off, avoid it. But here I didn't have to do any rounding. All right, roll a die. Find the probability of getting at least a 5. That means get a 5 or a 6. So 2/6 or 1/3. Higher than a 6. 0. It's impossible. If the probability is 0, it means it cannot happen. What if the probability is 1? 0 means it can't happen, and 1 means one. A probability of 1?
No, that's
a probability of 1 means it's happening. That's 100%. It's going to happen, right? Probabilities range from 0 to 1. Can't happen at all, absolutely will happen. And then all the other ones. At most, a 3. At most, a 3.
3 out of 6.
Here's your list.
3 out of 6.
3 out of 6. Because what does at most a 3 mean? It could be 3 or less. A multiple of 5.
1/6.
There's only one multiple of 5 up there, and so the probability is 1/6. Remember, a multiple of 5 means 5 goes into it evenly. All right, now we have a dartboard. We're gonna throw a dart at the dartboard. Here are the numbers on the dartboard. And we want to find the probability of throwing a dart and getting a number bigger than 1. Bigger than 1. How many of these numbers? I'm going to start right here. So bigger than 1 would be 1, 2, 3, 4, 5, 6. How many total numbers are there? 8. So your probability is 6/8, which is 3/4, or 75%, however you want to write it. I prefer fractions usually, but it doesn't make any difference as long as you're not rounding it off. All right, throw a dart at the board. What's the probability you'll get a multiple of 3?
1/4.
How many multiples of 3 are up here?
1, 2.
Is 3 a multiple of 3?
Yes.
Is 6 a multiple of 3?
Yes.
Are there any other ones? No. So B is 2/8 or 1/4. Again, a multiple of 3 means 3 divides into it evenly. An even number. An even number. How many evens do we have up there?
3.
4.
0.
3, 4.
4.
0 is an even number. 0 is considered an even number. What does it mean to be even? 2 goes into it evenly, right? What's 0 divided by 2? 0, no remainder. It's an even number. So there are 4 of them. So your probability is 1/2.
Yep.
Now, while we are here, I'm going to look at these 3 problems that these 3 problems that we just did. And I'm going to look at my probabilities as fractions. Those boxed in numbers are the probabilities, because now we're going to talk about odds. So we can do it right here in this same section. To the mathematician, odds is different than probability. Does anybody know mathematical odds? What we mean by odds? So, what was our definition of probability? Who wrote it down? Probability is successes over total. Successes over total. Odds are successes over failures. So probability is what you want over the total. Odds are what you want over what you don't want. Okay? So if we're back to problem A, and I want to know what are the odds of getting a number higher than 1. Okay? The probability was 6 numbers higher than 1 over 8 total. So if there are 6 numbers higher than 1, how many are there not higher than 1? 2. So that, the odds, I'll do the odds over here. The odds would be 6 over 2, which reduces to 3 over 1. And a lot of times, odds will be written like this. Have you ever seen that? Especially if you're looking at horse racing or something, you'll see odds written this way. Now, what this means is that if you did the experiment 4 times, you'd win 3 times and lose once. That's what odds mean. This is when you get what you want or win the game, and this is when you don't win the game. All right, so let's look at B. B was, I wanted a multiple of 3. So you told me from the field there that there were 2 multiples of 3 out of a total of 8? So if we're doing odds, if there are 2 multiples of 3, then how many not multiples of 3 are there? 6. So this is 1 to 3, which means your odds are 1 to 3. Now these say something totally different. This one says if you play it 4 times, you're going to win 3 times. This one says if you play it 4 times, you're only going to win once. So odds mean what you want, what you don't want. So there are 2 numbers you do want, and there are 6 numbers you don't want. There are a total of 8 numbers. So when you do probability, your denominator is the total. That's why it's an 8 for the probability. Okay? Now let's do C. You said you needed an even number. You said there were 4 evens and a total of 8. So what would the odds look like? 4 evens and 4 not evens, or odds? So that reduces to 1 over 1, and it might look like this. Now, what does that mean? If the odds are 1 to 1, it means you have the same chance of winning as you do of losing, which is what a probability of 1/2 means, right? Right? So 1 to 1, those are called, ironically, even odds. It means you have the same chance of winning as losing if something's 1 to 1. Okay? All right. So we're going to have to be careful, not on the quiz, the next quiz we take, but after that, we're going to have to read very carefully because the concepts are similar, but probability is different than odds. So if it says find the probability, you'll do success over total. Find the odds, you'll do success over failure.
I'm just curious, how do fight odds work then?
I don't know. That would be a good Google question. Okay, number 3. I'm talking as a mathematician, not as a.
Well, like, you know what you said, like the Vegas odds, it would be like negative, like 300.
I'm not even gonna worry.
Well, then maybe that's just
I don't want to do this. We're going from a purely mathematical standpoint. I don't know what they base all that stuff on. That's a question for Google. All right, number 3. A coin is flipped 14 times. What is the expected number of heads? I heard somebody say it. 7. Tell me how you got 7. Hannah? So what you're saying to me is the probability of getting ahead would be 1 over 2, right?
Yeah.
That's the probability. I want to try this experiment, flip this coin 14 times. So I have 14 times 1/2. So that gives me 7. Most of you got that without doing anything complicated. It doesn't get any harder than that, so just that's what you do. Those of you that are struggling a little bit with the concept, this is called expected value. How many did we expect? We're like predicting the outcome, and it's real easy. You take the probability of whatever it is you want to happen. In this case, we want to get ahead on the coin. And then you simply multiply it by the number of, we call them trials. So that is the number of times you're going to do something. Okay? So here's another example. Let's say you take a 10-question multiple choice quiz. Okay? And there are A, B, C, D choices on the quiz. You randomly guess how many can you expect to get right just from randomly guessing? Well, what's the probability you'll guess correctly? 1 out of 4? How many times are you guessing? 10. So what's 10 times 1/4? 2.5. So with random guessing, you can expect to get between 2 and 3 correct. Just random guessing. Okay?
What if you like do like
So let's, now these can get very complicated. We aren't doing anything complicated at this point. Let me give you one more example. Let's suppose that there are 3 numbers and a half. So we'll say the numbers 1, 2, and 3 are and a half. Okay? You're gonna pull a number out, put it back, pull a number out, put it back, pull a number out, put it back, and you're gonna do that 20 times. How many odd numbers can you expect? No. Because what with these numbers in the half, what's the probability of getting an odd one? 2 out of 3, right? And how many times am I doing that? 20. So how many odd numbers can I expect to get? 13 point something, right?
yeah.
So between 13 and 14. So how do we find the expected value? We take the probability of what it is we're doing, and we multiply it by the number of times we're going to do it. So in our original problem, the probability of getting ahead was a half. We're doing it 14 times, so 14 times a half was 7. Okay, one more question, number 4. The probability of a student being absent is 0.05, unless you're Sam, and then it's 0.5. All right, so the probability of being absent is 0.05. If there are 531 kids in the school, how many would you expect to be absent on any given day? Stop right there. How would we figure that out? Take the number of kids, which is 531, and multiply it by 0.05. So tell me what you get when you do that on your calculator. So about 26 to 27 kids, right? Now, what assumption, probably incorrect, are you making? Can you think of it? Anytime you're doing probabilities and statistics, you're making assumptions that you just have to be aware of. Mikey? Exactly. And I bet that if I did this experiment the day before spring break, I bet it's going to be more than this, right? But maybe if I did it on the first day of final exams, it would be less than that. So very good. Anytime we're doing this kind of stuff, we're making assumptions. We just have to be aware of that when we're analyzing the data. Okay?
It's just like what the average should be.
Exactly. Yep.